In this video, we'll look at the fundamental theorem for line integrals, which is a nice generalization of the fundamental theorem of calculus. That part of it in which you have the integral, the definite integral of the derivative of a function being evaluated by the difference of the function's values at the boundaries. So let me first state what the theorem says. So if C given by the vector function RT, a smooth curve given by this differentiable continuous vector function with t changing between a and b, if C is a smooth curve like that, and f of xy, let's stick with two variables for the time being. We could formulate the same thing for three variables, and this function is differentiable and continuous along this curve. And along C. If this happens, then the line integral of the gradient field, the gradient vector field corresponding to f along this curve C is simply given by the difference between the values that f takes at the endpoints of this curve. So this is the value f takes at the endpoint of the curve at RB, and this is the value it takes at the initial point RA. So the integral is evaluated by basically just this difference. The value of this integral is just this difference between the function's values at the endpoints of the curve. So imagine we have some curve. This is RA. This is our curve. This is RB, that point. And when we integrate this gradient field along that curve, all it matters is what the function is taking as values at the endpoints. So just to give you a short proof of this theorem, so remember what it means to compute such a line integral that we have here. So the gradient field of f integrated along C, what it means is we integrate from a to b with respect to t the gradient vector of f at xt, yt. It's dot product with r prime of t dt. So what's this dot product? Well, if we have the gradient, that means we have to take the vector consisting of the partial derivatives of f. So that dot product will be f sub t xt yt, and it's multiplied by the first component of the derivative of r. So that will be just dx over dt plus the second term in the dot product is the partial derivative of f with respect to y now, evaluated along the curve, multiplied by the second component of the derivative of r, which is y differentiated with respect to t, and this is what we integrate with respect to t. Now if you look at this integrand, what you notice that this is just the derivative of f with respect to t. because you may recognize that this is just a chain rule applied if we want to differentiate f with respect to t. So this integrand is just df over dt. So now we can simply apply the fundamental theorem of calculus, because we have the derivative of a function integrated. So that means that we can evaluate this integral by taking the value of f at b, at xb, yb, minus the value of the function at xa, ya. And this is exactly what we state here, because rb is xb, yb, and ra is xa, ya. So that concludes the proof. So there is a nice consequence of this fundamental theorem for line integrals, which is that if a function, and it's, well, if we take the gradient vector field of a function, then its line integral is independent of the path along which we integrate. As you can see, it's only the endpoints that matter, so it doesn't matter along which path we integrate, as long as the endpoints are the same. So it doesn't matter if it's this path or some other path, as long as we have the same endpoints, starting and endpoints. To say that again, we have path independence, so independence of path meaning that if we take the line integral along some curve C1 of this gradient vector field, the nabla f, and some other, and the line integrals along some other curve C2 of the same gradient field, it's going to be the same if these two curves will have, if C and C1 and C2 have the same initial and endpoints. Okay, just like in this drawing. And it's because both of these integrals are just this difference of between the values of f at the endpoints, so that if those endpoints, initial and endpoints, match, then both sides give you the same answer. So what we see now is that gradient vector fields have this independence of path property, and there is a theorem which says, that if a vector field capital F is path independent on some region D, then, which means that for any curve inside D, the line integral won't depend will only depend on the initial and endpoints, or in other terms, if the initial and endpoints coincide, so we talk about a closed curve, then the line integral will be 0. So path independence can be reformulated in that way, saying that a vector field is path independent if its line integrals along closed curves are 0. So if that happens for every closed curve in D, in this region D, then there is a function f such that the gradient of f is this vector field, capital F. Okay, so we can see that gradient vector fields are path independent, and if a vector field is path independent for every closed curve on a domain, then it is a conservative vector field, arises as the gradient vector field of a function. So that's one theorem. Another consequence of having a gradient field, so if f, so this is a separate statement, so if f is just the gradient vector field of some function, so the vector consisting of the partial derivative of a function f, which are the components of this vector field PQ, so P is f sub x and Q is f sub y, then of course, as long as we have second order partial derivatives and they are continuous, we will have the mixed derivatives be equal. So meaning that then the partial derivative of P with respect to y, which is just f sub x y, is going to be equal to f sub y x, which is the partial derivative of Q with respect to x. Okay, so then we have these this equality of the partial derivatives of the components of the vector field. Okay, so finally this is one direction. This is saying that if you have a conservative vector field, then the partial derivative of its first component with respect to the second variable is the same thing as the partial derivative of its second component with respect to the first variable. Now the reverse statement can also be formulated saying that if f is a vector field for which this holds, so that's a theorem, if for a vector field we have dp over dy equal dq over dx over a open simply connected region, which means that it's an open region which doesn't have holes and it is connected, it's in one piece and doesn't have holes in the middle, then on an open simply connected region D, then our vector field is conservative. Okay, so indeed, as long as f is defined over an open simply connected, by which I mean such a region would be simply connected and such a region with a hole in it is not simply connected. Okay, so as long as we have a vector field defined over an open simply connected region with these components, the partial derivatives of these components being equal, then we are dealing with a conservative vector field. Okay, so finally, let me just give you a question. So decide whether the following vector field is conservative. F has the components x minus y and x minus 2. Pause the video and select your answer below. Okay, I hope you paused it and what you realized is that this inequality does not hold, because if I differentiate the first component with respect to y, I get -1, while if I differentiate the second component with respect to x, I get +1. So indeed, these are not equal to one another, like in this theorem, so it's not conservative. Okay, so that's our first question. Second question, let F be the vector field with components 3 plus 2xy and x squared minus 3y squared. Okay, so pause the video and decide whether it's a conservative vector field or not. I hope you paused it and realized that it is indeed a conservative vector field, because we have this inequality between the partial derivatives of its components. The partial derivative of the first component with respect to y is 2x, and the partial derivative of the second component with respect to x is also 2x, and also F is defined over the entire plane R2, which is an open, simply connected region. So this theorem can be applied to this vector field and to deduce that it is conservative. And in fact, I can give you a function whose gradient vector will be exactly this capital F, and that function could be 3x plus x squared y minus y cubed, for example. And if you compute the gradient of f, of little f, you will get capital F. So it's a conservative vector field. Okay, I hope you enjoyed this video, and I'll see you in the next one.